So, good morning, good afternoon, and good evening. Hope you are all doing well and staying safe. I'm Mariam Shref, a senior petroleum engineering student at the Lebanese American University, and I'll be moderating today's session. So, on behalf of BioPetro, I want to welcome you all to our session about natural gas lab experiments. I hope that you have been enjoying and benefiting from this training so far. So today's lecture will be presented by a special guest speaker from Marietta College, Professor Chris Jacobs. Professor Jacobs is an adjunct professor at Marietta College and a professional engineer. He has been teaching since 2004 and is primarily involved with teaching the petroleum lab courses, core lab, drilling, and natural gas. He also teaches Marietta College's Fundamentals of Engineering Review course. He has extensive knowledge in energy systems, specifically solar photovoltaics. So please join me in welcoming Professor Jacobs. So we are pleasure to have you with us today. And on a final note, if you have any question related to the technical content of the presentation, please feel free to drop it down in the Q&A section, and we will sure try to address as many questions as possible at the end of this session. Without any further ado, Professor Jacobs, the mic is yours.
Well, thank you. Thank you for having me. So as we mentioned, we are going to talk about measuring the specific gravity of natural gas. If I get my slides to work here. Okay. So why do we want to measure specific gravity of natural gas? What's the purpose? What can we gain from it? Well, I listed 4 things we can learn based on a specific gravity if we know the specific gravity. One of them is the gas composition. We can estimate the gas composition. If we know the specific gravity of methane, then we can compare the reading we get from our measurements and determine whether or not we have mostly methane, we have some methane. Now, this is only going to be a rough estimate because if it's higher or lower than methane by more than, say, a few specific gravity points, then we don't know exactly what's in there. But if it's close to the specific gravity of methane, we can make a rule of thumb estimate that this gas content is fairly close to methane. We also can compare the specific gravity we obtain with the specific gravity of natural gases that have a known composition. However, one should be careful with that approach because just because 2 gases have the same specific gravity does not mean they have the same composition. So again, we just use this as a rule of thumb, as we say, to get a rough estimate of what the composition could be. A gas chromatograph would be a much better way to determine the composition of a natural gas, and that will be the topic for a future lecture. But again, you can estimate the composition from specific gravity. And I would not use this type of estimation for something like a custody transfer, where you need to be accurate. The second point that I have here, why we want to measure the specific gravity of natural gas, is then we can calculate the gas density at various reservoir conditions. Remember, we use gas has a PVT relationship, follows the ideal gas and real gas laws. And because gas is compressible, we need to follow the ideal gas and the real gas laws. So if we happen to know the reservoir temperature and reservoir pressure, we can calculate the gas density at reservoir conditions at any point in the reservoir. If we know the temperature and pressure at one point in the reservoir, we can calculate the gas density there. If we know the temperature and pressure at a different point in the reservoir, we can calculate the gas density at that point. The third thing we can measure, if we know the specific gravity, is we can determine the gas viscosity. If we know the temperature again, and the molecular weight, which is related to the density, we can calculate the gas viscosity. And this uses the Lee method or the Lee equation to do so. And there is an advantage if you want to use the Sutton method. You can actually calculate the density, the gas density, and the viscosity with condensate reservoirs, which is also very important. The last reason that I have on my list, again, this is not an all-inclusive list, this is just some of what I think is important, is we can measure the pseudocritical properties, pseudocritical temperature, pseudocritical pressure. Now remember, pseudocritical properties are gas mixtures. And we estimate them using a graph. Brown in 1948 developed a graph that can extrapolate these pseudocritical properties. And this is an approximation when we know the specific gravity. Now, just as a reminder, the critical properties, the critical point is the point where the bubble curve meets the dew point curve. And at that given pressure and temperature, the gas properties are identical to the liquid properties. So if we know the pseudocritical properties, then we're basically, it's the critical properties for a gas mixture. So as you can see, we can use specific gravity to determine important gas properties, which is useful from a reservoir or production standpoint. So we have several methods that we can measure specific gravity with. Now, I will say that this is not an inclusive list. I'm only going to talk about a few methods here. There are others that can be done in real time. Most of these are designed to be done at a single point in time. So these are just 4 of the ones that I'm going to cover today in this part of the lecture. So the first one I have is called a gravity balance, which follows the effusion and weighing technology. Now, a gravity balance operates on the principle that we measure the pressure exerted by a gas of a given density and the pressure exerted by air of a known density. That means specific gravity is a ratio of those two pressures. And perhaps another way of explaining that, the word effusion means we take 2 equal volumes of gas. One would be our natural gas sample, one would be our air sample, both at the same pressure, exiting through the same size small orifice at the bottom. And the time required for that fixed volume of gas to escape is approximately proportional to the square roots of the densities. The gravity balance is a very accurate device, a very accurate way to measure the specific gravity. However, it does take a fair amount of time to obtain the reading. So if time is of the essence, there are other options that might be better. The second one on my list is called direct weighing, and that is also a balance type system. It uses a simple balance beam to measure specific gravity. Once again, we have 2 identical tanks. One would be the reference tank, which would be air. The other would be the sample. We would hang them on a balance that is equidistant from each other. So it basically would balance. When both of those tanks have air in them, they both have the same weight and therefore are balanced. Once we purge the air out of the sample tank and we place that with a natural gas, obviously the buoyant force of air is going to be different from the buoyant force of the gas, which will tip the balance, and the needle will slide to one side and report the specific gravity. In this direct weighing technology, both the tanks are made of the same material, so the temperature of the air and the temperature of the gas are going to be identical. We said we're going to pressurize them to the same pressure, so both of them will be identical. And any ambient changes to either one of those will be observed equally by the tanks. So that will nullify any impact of ambient conditions. The third option I have on my list is gas chromatography. And I mentioned briefly that gas chromatography is a much better way to determine gas composition, because the way we use chromatography is we run a gas sample through a chromatograph, and that sample is physically separated into its individual components and quantified. So not only do we know what components are in the gas sample, we know exactly what percentage of each of those components makes up the gas sample. So the theoretical specific gravity would be the sum of the specific gravities of each component, which the specific gravities of each of the component gases are known, multiplied by the mole percentage of that component. Now, I will mention most chromatographs are C6 plus chromatographs. So the hexanes and heavier gases are pulled out as one. So you're not going to get a composition of those heavier gases, those heavier components. However, again, in most natural gas, the C6 plus, the hexanes and heavier are less than 1%. So it really is not going to be a significant amount. And finally, and this is what I'm going to spend most of the lecture today talking about, is the Ranorex gravitometer, which operates on the kinetic energy principle. And I will go into more detail about how that particular piece of equipment works during the rest of this lecture. Before we get into measuring specific gravity, I'd like to do a little review of what specific gravity is. Now you can see from this equation here, specific gravity is the ratio of a density of a material to the density of some reference material. And because it's a ratio, it has no units. It is a dimensionless quantity. It's just a number. There are no units associated with it. Now, when we're talking about the specific gravity of a liquid or a solid, our reference material is water. However, when we want to measure the specific gravity of a gas, we use the reference material of air. In order to do this accurately, we have to have the air at a normal temperature and pressure, which is 20 degrees Celsius and 1 atmosphere. If we are measuring air or our gas, and either one of those are not at the normal temperature of 20 degrees Celsius and 1 atmosphere, we will not get an accurate comparison between the two, and therefore the density will not be accurate. So it is important to measure specific gravity at the same temperature and pressure for both substances. And I alluded to that briefly before with how the gravity balance works and the other balance systems, direct weighing. So this is an example of what the Ranorex gravitometer looks like. And I have a video at the end that I will show you that it shows how this machine works. But I'm just going to go over a few key components here. So if we look at this machine here, this is a portable machine. This can be used in the field or it can be used in the lab. It weighs about 37 pounds, 17 kilograms. It's about 12 inches by 12 inches by 10 inches. Unfortunately, I did not convert that to metric, so my apologies, but it is a fairly small machine for all practical purposes. It is a little bit on the heavy side, however. Now, it normally runs off of alternating current, or AC. If you want to use it in the field, you must use an AC-DC inverter that converts the DC from your vehicle into AC to use with the machine. And Chandler Engineering, the Ranorex manufacturer, has such an inverter. I believe any commercial inverter that will support the proper current and voltage can be used. But it's very important that whatever inverter you're using can produce enough voltage and current to operate this equipment. Next thing I'd like to call your attention to here is this plastic box here. This is the air dryer. And I mentioned that we need to have air at 20 degrees Celsius and 1 atmosphere. And it also needs to be dry. And I'll talk a little bit more about the air dryer in the next slide, but I just want to point this out here. This is the air dryer. All right, now moving along, this is the selector valve here. So there are 3 positions on this selector valve. There is a 0 position. There is an HG for gases that are heavier than air. An LG position for gases that are lighter than air. This right here, this is the gas inlet valve. This is where we will have the gas coming into the gravitometer. This is a ball style flow meter. So we can adjust the flow rate of the gas coming in there. This is how we adjust it right here with this knob. Now this flow meter actually measures, or is the marks on the flow meter are in specific gravity units. And that's allow us to set the flow to the approximate specific gravity of the gas. Obviously, if we knew the exact specific gravity of the gas, we would not need to use the gravitometer. The next thing I want to call your attention to is this lock-unlock switch. Because the internal components are precision components, we do not want to have the needle be jostled around or bounced around while we are transporting the unit from one location to another. So we always want to make sure that the needle is in the lock position. When we want to go use it, we're going to move it to the unlock position. And I will show you, and again, you'll see this in the video exactly how this works. The needle, when it is in the lock position, is right behind this label. You cannot see it now because it's behind this label. This label is actually the directions on how to operate the machine. So it is not necessary to bring the manual with you. It is not necessary to memorize anything. You can just look at the label and it will tell you how to use the machine. When I turn the lock knob to the unlock position, the needle will come down from here and it should stop right here at the 1.000 mark. Okay. So when I first turn the machine on, it's pulling air through both of the chambers. It should read 1.00. If it does not, we have the ability to adjust the 0 mark. Now you will notice that this particular dial here, this dial indicator, has red numbers on the inside and black numbers on the outside. The needle always will move in this direction. I mentioned we can use the gravitometer to measure gas with a density of less than 1 and a density greater than 1, lighter than air and heavier than air. The red scale on the inside is for gases that are lighter than air, so it goes from 1.000 all the way down to 0.550 and below. If I was measuring a gas that was heavier than air, it would go from 1.00 on the outer scale. On the black dial, you can see it goes all the way around here to 1.80. So we can use the same machine to measure two different types of gases, heavier than air and lighter than air. And the one thing that is not shown in this picture that you will see in the video, there on the gas outlets are on the side of the machine that is not visible. So this back side of the machine right here. Again, we have, because we can measure gases that are heavier than air or lighter than air, we are going to have two gas outlets, one for the heavy gas and one for the light gas. Now I mentioned the air dryer and what the purpose of the air dryer is. And this is a picture of the desiccant. Desiccant means it's an air dryer. It dries the air, removes humidity, moisture from the air. Now, this is the desiccant. The desiccant is stored inside this plastic case right here. All right. Now, when you look through the window from the side, you're not going to see all four of these colors. This is just a representative diagram to show you what the desiccant would look like at different stages. And I mentioned that in order for air to have a specific gravity of 1, it must be dry, meaning it must have no moisture in it, because moisture will change the density of the air. In order for us to get an accurate specific gravity, our reference material has to be at the standards for air, which is dry, 20 degrees Celsius, and 1 atmosphere. So we have to remove any moisture that might be in the air, from the air. Otherwise, we will get an incorrect reading. Now, these are fairly small particles. This is about 1 to 2 millimeters in size here. These are not very large particles. And when it says deep blue color right here, that means that this desiccant is completely dry and is active. That means it can be ready to be used to remove moisture from the air. As it starts to move moisture from the air, it will start to get some pink in it here. We go to the third column. You can see it's mostly pink with just a little bit of blue. And this far column over here, this is pink. This is basically almost completely saturated. So we always want to have the desiccant to be this blue color, or possibly we can use it with just a little bit of pink. If we start getting, when we're ready to run the machine, if we start running it and it is this pink color, it is very likely it will not be able to remove all the moisture from the incoming air, which means that we will not be running at the proper base normal temperature and pressure for the air. The reference material will not be at the standard conditions. Now this is a silica gel desiccant. Even though it says it's a gel, it's actually crystals. Like I said, they're about 1 millimeter, 2 millimeters in size. This is a reversible process. So once the desiccant has been exhausted or fully saturated, you can remove it from the machine and you basically just reheat it to about 120 degrees Celsius, and you are driving the moisture back out of the desiccant. And as the moisture is driven back out of the desiccant, it will turn from pink back to this deep blue color. So once you have the desiccant is all, or 90% of it, 95% of it, most of it is this deep blue color, it can be placed back in the machine and used again. So, and it's continuously reusable. Now I'm going to go back. When you want to remove the desiccant from the machine, you remove these two thumb screws, and this whole plastic box will slide out of the machine, and there's a hose behind it that's maybe 10 centimeters long, so it's flexible. You remove this plug, and you can just pour the tilt this down this way. You can pour the desiccant out into some kind of a pan, put it on a open top burner, not a Bunsen burner so much, but like a hot plate or a stove, and you heat it back up. It may take 15 minutes. Once all the desiccant is blue, you can use a funnel. You can pour it back in through this hole, put this connection back on again, and you are ready to use the machine. Now the air is pulled in through small holes in the bottom here. It goes up through a grate that you cannot see, and then it goes through the hose into the machine. So once it goes through the desiccant, it is in a sealed chamber, so no more moisture will be able to get to it. Okay, now I mentioned that in order to have an accurate comparison, we need to have both the air and the gas at ambient temperature and barometric pressure. That's to do an apples to apples comparison. Obviously, we are pulling air in at ambient temperature and at barometric pressure because it's coming from the environment in the room, in the lab, in the field. How are we going to control or adjust the temperature of the gas and the pressure of the gas? Well, you can set your gas flow rate to about 12 CFM, and that will adjust the pressure to barometric pressure, approximately close enough to barometric pressure that the results will be accurate. Okay, now we've got the pressure taken care of. Well, what about the temperature? What about ambient temperature? Well, we have a copper coil that we attach to the gas inlet, and it's 3/8 by 5 feet, so it's about almost half a centimeter, not quite half a centimeter by 1.5 meters. And the gas will pass through the copper coil before it enters the gravitometer. And this copper coil acts as a heat exchanger. And copper is very good at heat transfer. So if the gas going into the machine is hotter than the ambient air, as it passes through the coil, it will release heat to the atmosphere, and the temperature by the time it reaches the 1.5 meters at the end of the copper coil, or before that, it will be the same temperature as the air. Conversely, if the gas is colder than the air, then the heat will be absorbed by the copper tubing and heat the gas up to the same temperature as the air. Now, the last bullet point here about this inlet filter, that is not related to the ambient temperature and barometric pressure. However, that is an important thing. We need to have an inlet filter on the machine so that we do not pull contaminants into the operating side of the machine, which, as I will show you in the next few slides, how the machine works, you will get a better understanding of that. If you are planning on testing or measuring like a commercial household gas that's already been processed, probably not necessary because that gas is fairly clean. But if you're going to use wellhead gas or reservoir gas, you want to have a filter on there to eliminate any kind of contaminants. And again, contaminants like moisture will affect the density of the gas. So how exactly does this work? How do we determine the specific gravity by using two gas streams? So this is an interior diagram of what's inside the gravitometer. We have two gas-tight sealed chambers here, identical. We have one here. We have one at the bottom. And they both have separate inlets and outlets. So for example, the air would come in on this side over here and go out here. The gas will come in on this side here and go out here. So there is no connection between these two chambers. They are both independent. You can see on the right side here, we have an impeller wheel. Both chambers have an impeller wheel. When you first turn the unit on, a motor will start and turn these belts at exactly the same speed. So both these impeller wheels are turning at exactly the same speed. The impeller wheels are what pull the gas and the air into these chambers. Both these impeller wheels turn the same direction. You can see they turn here, in this case, in the upward direction. Now, I'd like to call your attention to the fact that this looks like this is a continuous shaft through these gas-tight chambers. However, these are not the same shaft. This shaft only turns this wheel. There is no connection between this wheel and this wheel. So this wheel over here is called the impeller. This wheel on this side is called the impulse wheel. The impulse wheel is connected by a separate shaft to the measuring arm here. And because there's no connection here, this operates as a fluid coupling, which is very similar to your automatic transmission. As the gas or air is pulled into these chambers and it's spun through this wheel, the force of the gas spinning will transfer as it fills this gap and then impinge on the impulse wheel and start turning the impulse wheel. And in the next slide, I will show you exactly how we measure the specific gravity based on that. But it's very important to understand that these two wheels are not connected by anything mechanical, strictly by fluid. It's fluid coupling. And as we remember from fluid mechanics, that air is actually a fluid. Gas is a fluid. So here's how we actually can use this principle to measure specific gravity. When I first turn the machine on and I have it set for the 0 position, I am pulling air through both of those airtight chambers. And as I mentioned here, the air will come through and it will turn these impellers, or the impellers will turn here, will pull the air through, and through that fluid coupling will impinge on these wheels. I now have air on this wheel and I have air on this wheel. So what happens is now I am pulling the wheel through the shaft. Like I said, this shaft is connected directly to this measuring wheel, directly here. As the impulse wheel is turning, it is generating a torque on this measuring wheel. The impulse shaft on the lower chamber is generating a torque on the reference wheel. When we are using air, we should have the same torques because it is the same material. In order for the torques to be the same, remember torque is force times the perpendicular length. In order for the torques to be the same, this RA is the same as this RA, and FA is equal to FA. They are now in static equilibrium. They are balanced. As we start emitting gas, we have now turned the gas valve to say LG, less than air. The torque for the air is still going to be the same. The torque produced by the gas, because it has a lower density, is going to apply less force on the impulse wheel. The torque on the gas is going to be less. So these two wheels are connected by this tape over here. This tape right here, it's a metal tape. So these two wheels are connected. Because this torque is larger, using the same principle of torque is equal to force times the perpendicular distance, FA is now larger than FG, so it starts to pull this wheel down. As it pulls this wheel down, you can see that this measuring wheel is an eccentric. You will notice that the radius changes as it rotates along this surface here until it gets to a point where the torque times the radius now can produce, with a shorter radius, the gas force has to be larger to produce a torque. And then now Fg is equal to Fa. Temperature and pressure are equal, and the motor speed on the inlet side is equal. So the only thing that is changing is that force. So we're comparing the torque of one to the torque of the other. We're comparing torques, and that's how it works. So going back to this other picture here, you can see the two wheels here. This is the measuring wheel. This is the one that looks like a eccentric, and it's attached to another shaft that goes down to the needle, and the needle moves along the gauge. So that's a very simple process of how it works. So remember, it is the torque that makes the adjustment, not necessarily the forces. So how do we actually use the machine? I'm just going to go over this briefly in a discussion form, and then I will show you the video. The first thing you want to do, obviously, is to power the unit up. If you're using AC, you plug it into your AC supply. If you're using DC, you first power up your inverter. Once your inverter has been stable, operated a stable condition, then you will plug in your AC to your inverter. You'll then unlock the machine. As I mentioned, you unlock it from this position over here. And what happens is the needle will start drifting down towards 1.00. Now, it will take some time to do that because we talked about how the air coming in or the gas coming in has to impinge on the impulse wheel. So it takes some time for that to build up to a normal operating speed. The impellers are operating at a fixed speed, but to transfer that energy over to the impulse wheels will take a few seconds. The chambers have to fill with air. Once that happens, we basically are expecting to get our pointer to read at 00 because we are now measuring air through both of the chambers. If it does not read 00 after maybe 30 seconds, you adjust this 0 right here and you set it to 00. Now you know both chambers are accurately recording the same specific gravity. Okay. The next thing we will do, and we're assuming that our gas is already hooked up over here. Obviously, we want to make sure the gas is hooked up before we turn the machine on. But generally, we want to have the gas hooked up and with the proper filtration, and the copper coil will be attached here. The next thing we will do is we will turn the selector valve to either HG if it's a gas heavier than air, or an LG if it's a gas lighter than air. And we will adjust the flow meter to the approximate specific gravity. Like I said, this is a ball style flow meter. The ball is right here. In the video, you'll see it move up to a location, which is about the specific gravity. So you can see how that works. Now, it'll take maybe 10, 20, 30 seconds for the specific gravity to start moving in this direction, for the needle to start moving in this direction. Because remember, the chamber is filled with, both chambers are filled with air. We need to purge out the air, replace the air with gas. So the gas has to come in and it's going to replace the air that's in the chamber, and it's going to take a while for it to start to come in and impinge. Once it starts to read the specific gravity, so it may take 15 seconds for it to go from, in this case, 1.00 to 0.950. Once it gets to this point, it will start fairly quickly to move in the direction it needs to go. Once it gets into an area that's closer to the specific gravity, it will slow down again. And it may take a little bit of time, again, to finally reach the stable point of the specific gravity. So you want to let the pointer to stabilize. Don't write down the first value you see and say, I'm done. You know, let it stabilize, and you can write down what the specific gravity is. Now, again, the second thing I want to say about this is you always want to do more than one trial. Now, obviously, in order to do an accurate trial, you should completely go back to the beginning, but you don't want to just run one sample through it and says, I know what my specific gravity is, especially if you're talking about, reservoir gas. You want to pull a sample, maybe wait 10 minutes, pull another sample, whatever your company dictates. You want to make sure that you're getting an accurate representation of that particular gas, not just a single sample. Once you are done measuring the specific gravity, and you're over here at this point somewhere, let's just say for gas lighter than air, you will again turn the selector valve back to 0. The needle will come back to approximately 1.00. And again, the same thing will happen. It's going to take a little while for it to start moving because you need to purge the gas out with the air. The needle will now go up to 1.00 or 0.99. Very important, before you turn this lock mechanism back to lock, the specific gravity or the needle has to be very close to this 1.00 mark, because otherwise the lock mechanism will not be able to engage the dial mechanism and lock it. And that, again, that can be bad, because if you are using this out in the field and you do not lock this and you pick it up, and you've seen how precise those wheels are, the measuring wheels, if you get them out of adjustment, you'll not be able to measure the proper specific gravity. So I am now going to show you a video of this in operation, and you can get a better working understanding of how it works and exactly what happens during each of the stages.
I'm going to demonstrate the use of the Ranorex gravitometer that I talked about in the lecture. Now, as you can see it, I want to review a few of the key components to it that I did mention in the lecture. So we have, this is a desiccant chamber here. And as you can see, it's this very deep blue color. And the way that it works is it pulls air in through these holes in the bottom, and then there's a grate, and then it works its way into the machine. So we want this to be that nice deep blue color. That means the desiccant is active and ready to be used. This is a selector switch that we're going to use to determine whether we're going to put a high specific gravity gas or a low specific gravity gas. And as you can see, this is the flow meter. So the first thing I want to do when I'm ready to use the equipment is I will power it on. And I want to make sure that the selector valve is set to 0. Now, what you can hear right now is you can hear the motor in there that is turning both of those sets of wheels at the same speed. First thing we're going to do is basically what's going to happen. I'm now pulling air through both sides of the machine. When I move this unlock switch to unlock and I unlock the needle, you will see the needle come down from its lock position, which is just up inside past this label here. Because I am pulling air through the machine on the measuring side and air through the machine on the reference side, I should be getting a specific gravity of 1.00. May take a few seconds for it to get to that point because it has to purge out everything that was in the machine in the first place. So we wait a few seconds here. We'll notice that the air is coming down. Looks like it's just above 1. So I want to let it get to 1.0. If it turns out that it is not at 1.0 after we're done letting it sit, we have this 0 adjust mechanism. We can adjust it to exactly 0. So I'm going to adjust it to exactly 0 before we start taking a reading. Okay. Now that I have done that, I want to call your attention here. I'll turn the gas on. I want to mention a note about this copper coil. I mentioned this in the lecture. This coil is used as a heat exchanger. We talked about that the gas and the air have to both be at ambient temperature. This coil allows us to do that. If the gas is warmer than the air, it will release heat to the air. So now both are at the same temperature. If the gas happens to be colder than the air temperature will interact with the gas in the copper tubing here and make it air temperature. That way both the temperatures are the same, because that was one of our requirements. It had to be same temperature. Okay, so now what I'm ready to do is to actually measure the specific gravity of the gas. I will turn this selector valve to LG, which means low gas or specific gravity less than 1. Okay, and you'll notice that the flow meter went up to about the specific gravity of what I thought the gas was going to be. Now the needle moves down the scale here until it gets to whatever the specific gravity is. Now, 2 things I want to mention about this. Number 1, when you first turn it on, remember the gas has to purge the air that was in that measuring chamber before it can start analyzing the gas itself. So it may take a few seconds for the needle to drop from 1. In this case, we're using the inner scale, the red scale here. This is the one for gas with a specific gravity of less than 1. It may take a few seconds for it to come down to say 0.95 as it starts to purge the air out. And then it will fairly quickly move around to approximately the specific gravity. And then you want it to stabilize. Once it stops moving and stabilize, you know what the specific gravity is. So I will read that right now. It appears to be stable. It's just about 0.6. So now we know the specific gravity of this gas sample is 0.6. So now what we would want to do, once we've measured the gas sample, again, we will turn the selector valve back to 0. And again, you're going to have the reverse happen. Now you're going to purge the gas out of the gravitometer. So once it starts purging, it will start moving back down the scale, back up the scale to 1.0. Now, in order to lock this needle up again, we have to have this pointer very close to the 1.0. Otherwise, the locking mechanism cannot engage and safely put the needle up inside the machine and protect it. So it's made, again, just like the reverse, it takes a while to purge, and then it has to balance itself out. It does not have to be exactly 1.00. It is best if it is 1.00, but if it gets close to 0.9899, I can engage the locking mechanism, and it will pull the needle back up inside the machine. One thing I will mention about the needle, this needle does not have a parallax mirror on it. So it's not like you can line it up exactly across like you would do with some of the meters where there's a parallax. So the parallax effect is not necessarily an issue. However, this needle has a very flat surface. So you can look at the needle cross and then you can read the specific gravity directly off of that. And if you look and see from the scale over here, we have 1.00 at this location and 0.9500. So each of the major indicators is 0.01. So you don't have to be exact with worrying about parallax in this case. Now it appears that the specific gravity is now back to 0.99, which as I mentioned is sufficient to engage the locking mechanism. So I will turn the locking mechanism back to lock. You'll see the needle retreats back up inside the machine and it clicks. That means it's locked. So when I transport this, that needle mechanism is not going to bounce around inside the machine. That is the safest way to do it. You always want to make sure you have it locked whenever you are not using it. I will now go turn the gas supply off over here. And we are done using this equipment to measure specific gravity. I'm going to unplug it. As I mentioned in the lecture, this is actually a portable unit. You can see I will pick it up here. It's not especially heavy. It's a little bulky, but it is portable. However, you need to have an inverter in your vehicle or whatever location you're going to use this in order, because this is an AC equipment, piece of AC equipment. So you need an inverter that will convert from the DC supply of your vehicle to AC. Otherwise, operation is exactly the same whether you're using it in the lab or out in the field. So I hope this actually helped you visualize the operation of the Ranorex gravitometer, and I really appreciate your attention. Thank you.
Okay, I hope that was useful for you. And again, if people have questions, I'd be happy to answer them as best as I can.
Thank you for this informative session. Now we'll begin by addressing some questions. So the first question is that, how can I know if this is a low or high grade gas? I think he was asking about the experiment while you were doing the experiment.
Okay, so the question, if I'm understanding it, is how do I know if I have a gas that's heavier than air or lighter than air?
Yes.
And that's actually a good question. A lot of it comes from knowledge of the field you're working in. If you know that the field you have is a lighter gas or a heavier gas, I'm going to say most of the gases that we work with are going to be lighter than air. Some of the condensates may be heavier than air. That is a good question. And I'm not exactly sure how you would determine that. You'd almost have to find out from basically the production guys or ladies what you want to use for that. It's possible also to run it through, I'm not saying a chromatograph because you can get the specific gravity that way. This is more of a portable type unit, so you're more likely to use it where you know whether the gas is a heavy gas or a lighter gas. So I hope that answers that somewhat satisfactorily.
Yes, it does. Thank you. Now the second question is that why did the designator color not change to pink in the video?
Okay. The desiccator will change to pink depending on the amount of moisture that you use. When I was talking about the colors, the various colors of the desiccator, I'll go back and look at that here. Okay. These colors are reference colors. These can absorb a significant amount of moisture from the air. These are not designed to go from blue to pink during one test. If the air content is fairly dry, then you will not be pulling that much moisture out of it. And the air down there was fairly dry. And what I did not show you from the experiment, but you could sort of see the depth of that desiccant case is almost as deep as the dimensions of the desiccator case. So for example, going back to this picture over here, this is the size of the chamber inside, which you can't see. And it goes back about this far. So it holds a lot of material inside of there. You're not going to see the color change during one test. For example, I had that machine. I was blue when I used it several months ago. And when I went to go use it when I made the video, it had been this color. So even over several months of sitting in a normal environment, it didn't pick up that much moisture. As long as it will change colors as it absorbs moisture. So if there's not a lot of moisture in the air, and we did not run the test for very long, I mean, that was a 7-minute video, it would not likely to pick up enough moisture to change it all the way to pink. My point is don't just take the machine. If you use the gravitometer, say this week, and then you put it back in storage and you don't use it for 3 months, don't assume that this is going to be blue. You always want to check it to make sure it's not pink. So I hope that was a good answer to that question. It's not designed to be changing instantaneously. All it does is tell you that all you need to know about using it is once it does start to change pink, you know it cannot hold much moisture anymore.
Yes, great. Now we have another question. Is there a chance to measure specific gravity of liquefied natural gas in liquid state?
Not with this particular equipment. If it's in a liquid state, you probably have to use a liquid gravitometer, because this is comparing a gas. When you're measuring the specific gravity of a gas, you're using air as your reference material. Dry air. So the liquefied, well, I know liquefied natural gas is compressed, but if you're going to compress it, that's going to follow your PVT principles.
Okay, thank you. Now the last question for today. What is the accuracy of the Ranorex instrument as compared to other methods?
As long as the Ranorex equipment is still, let's put it this way, if it's been properly calibrated, which it usually is calibrated when it comes from the factory, and it can be recalibrated, it is fairly accurate. However, it should be calibrated periodically to ensure that your readings are accurate. Now, compared to, like I said, the gas chromatograph, if you have a good representation of the individual components, that is fairly accurate too. So I would say the Ranorex is a fast way to determine specific gravity. I mentioned with the gravity balance, those take a long time, but they're very accurate. So I would say the Ranorex is very accurate. However, if you wanted to be extremely accurate, you might want to use one of the lab scale pieces of equipment, like the gravity balance or direct weighing. Those are extremely accurate.
Okay, thank you. Now to highlight, this session has been recorded. It will be uploaded soon on Biopetra's YouTube channel as usual. Now, as a reminder, please, for those who didn't join the Google Classroom for this training, please join as soon as possible and fill the personal information document with the same email you will be using for the upcoming quizzes and the final exam. Now, quizzes for previous lectures have been already posted, so please make sure to complete them before the assigned deadline. You can check the deadline on the Google Classroom, and the quiz for this lecture will be uploaded soon. Now, that's all for today. Thank you again, Professor Jacobs, for this informative session. I hope you all enjoyed this session. Best of luck. Have a nice day and see you in future webinars. Thank you.